Hello everyone, I'm Prakash Jain, Assistant Professor, Department of Mechanical Engineering, HIT Mangalore. Today I'm going to discuss about Module 4 of Fluid Mechanics, that is Dimensional Analysis. Syllabus, Introduction, Derived Quantities, Dimensions of Physical Quantities, Dimensional Homogeneity, Rayleigh's Method, Buckingham's Pi Theorem, Dimensionless Numbers, Similitude and Types of Similitude. Today in this video I'm going to discuss about Introduction, Derived Quantities, Dimensions of Physical Quantities and Dimensional Homogeneity. So first let's go for introduction. So what is dimensional analysis? Dimensional analysis is a method of dimensions. So it is used to determine dimensions of various parameters like independent variable or dependent variable. So it is what is the application part of this dimensional analysis? So it is used in research work for designing of any component or equipment and as well as in conducting model tests in order to obtain scale ratio of model with respect to prototype. Then it deals with the dimensions of physical quantities involved in the phenomenon or experimentation. So it is used to calculate or determine dimensions of various parameters involved in experimentation, namely dynamic viscosity, pressure, or area, length, or bulk modulus, so on. So all physical quantities are measured by comparison, which is made with respect to an arbitrary fixed value. So in order to make comparison, we should have some standard value. So these standard values in dimensional analysis are called as fundamental quantities or primary quantities. So length L, that is represented by capital letter L, mass that is represented by capital M, and time that is represented by capital T are three fixed dimensions which are of importance in fluid mechanics. Most commonly we are going to use only three dimensions in fluid mechanics, that is length L, mass M and time T. So in addition to mass M, length L and time T, we are going to use one more parameter, that is theta. So when to use that theta parameter? So theta parameter is used in heat transfer problem, like if the heat transfer is taking place from surrounding to system or system to surrounding, then temperature is the main parameter. So in order to replace temperature in SI unit, the SI unit of temperature is Kelvin, at replaced into dimension, that is theta. So four fundamental quantities, that is for mass M, length L, time T, and for Kelvin it is theta. So that are used in problems, but in this module we are going to discuss about only three fundamental quantities, that is mass M, length L and time T. Then secondary or derived quantities, as the name itself indicates, these are the quantities that are derived from primary quantities or fundamental quantities. So you can take into consideration of area. Area is given by length into breadth, also unit is meter square or side square. So meter is the unit of length. So the dimension for length is L. So L into L, that is L square. So that is area is derived quantity or secondary quantity. Then velocity. What is velocity? Velocity is given by density by time or distance by time. So unit of distance is meter and time it is second. Meter per second is the SI unit for velocity. So for meter, the fundamental quantity is L and for second it is T. So L into T to the power minus 1. There is a dimension for velocity. Then density. Density is equal to mass by volume. For mass it is kg is the SI unit and for volume it is meter cube. Kg by meter cube, there is a unit for density or kg per meter cube. So in terms of dimension it becomes m into L to the power minus 3. For we are going to replace kg by capital letter M and meter cube by L cube. Next, acceleration, that is rate of change of velocity. So otherwise it is the velocity divided by time. So unit of velocity is meter per second and time it is second. Meter per second divided by second, that becomes meter per second square. So dimension for acceleration becomes L into T to the power minus 2. So the expressions L by T, M by L cube and L by T square are called dimensions of velocity, density and acceleration respectively. This is the most commonly asked question. Give examples for secondary quantities. So you can take into consideration of any of these like velocity, acceleration, area or dynamic viscosity, anything. So because they are derived from fundamental quantities, those are like M, L and T. So dimensions of physical quantities. So the dimensions of mostly used physical quantities in fluid mechanics are given in table. So let's discuss one by one. So first physical quantity it is length. It is represented by capital letter L and dimension is L, capital letter L. Then mass, it is represented by symbol M, dimension is capital letter M. Then time, it is represented by symbol T and dimension is capital letter T. Next, geometric quantities. So these are involved with the shape and size of the quantities or equipment. So that's why they are called as geometric quantities. So first one is area. So it is represented by capital letter A, unit is meter square. So dimension becomes L square. Then volume, volume is actually area into length or area into thickness. So it is represented by small letter V and unit is meter cube. So meter, dimension for meter is L. So meter cube, in place of meter cube, we are going to get L cube as dimension for volume. Next, kinematic quantities. We have 7 kinematic quantities listed here. So first one, velocity, that is represented by symbol V, unit is meter per second. So dimension becomes L into t to the power minus 1. Then angular velocity, symbol is omega, unit is radian per second. Radian has no unit, per second, so that is s to the power minus 1. Second is replaced by t here in dimensions. So dimension becomes t to the power minus 1. Then acceleration, that is represented by symbol A, unit is meter per second square. So dimension is L into t to the power minus 2. Angular acceleration, that is alpha, unit is radian per second square, that is angular velocity divided by time. So that is angular acceleration. So radian per second square, again radian has no unit, so no dimension. So per second square or s to the power minus 2. So dimension becomes t to the power minus 2. Then discharge Q or volumetric flow rate, amount of fluid flowing per second. So that is represented by capital letter Q, unit is meter cube per second. So for meter it is L, so L cube per second, L cube divided by T. So dimension becomes L cube into t to the power minus 1. Then acceleration due to gravity, that is represented by symbol G, small letter G. So unit is same as that of acceleration, meter per second square. So dimension also same as that of acceleration. So dimension is L into t to the power minus 2. Then kinematic viscosity, there are 2 types of viscosity. First of all, we have to know what is viscosity. Viscosity is resistance to flow. So there are 2 types of viscosity. First one is dynamic viscosity. Second one is kinematic viscosity. So unit of kinematic viscosity is meter square per second. So the dimension becomes L square per T or L square into t to the power minus 1. So these are the kinematic quantities. Next, dynamic quantities. So these are involved with motion of the fluid or motion of the element. So first one, force. From Newton's second law of motion, we have expression for force as mass into acceleration. So unit of mass is kg, unit of acceleration is meter per second square. So overall unit for force becomes kg into meter into second to the power minus 2. So otherwise it is called as Newton. So dimension is m into L into t to the power minus 2, replacing kg by m and meter by L and second square by t square. Then weight, that is represented by capital letter W, mass into acceleration due to gravity, mass is m and acceleration due to gravity is g, m into g. So overall unit for weight, that becomes kg into meter into second to the power minus 2 or Newton. So this weight and force has same unit, that's Newton, and same dimension. So dimension for weight is m into L into t to the power minus 2. Next, density, that is rho, mass by volume, so m by v, so unit of m is kg divided by volume, that is meter cube. So dimension becomes, replacing kg by capital letter M, meter by capital letter L, so we get dimension for density as m into L to the power minus 3. Then specific weight, that is represented by, in some of the cases, small letter w, or it can be represented by Greek letter gamma. So gamma or W equal to rho into g, product of density into acceleration due to gravity. Unit of density is kg per meter cube. Unit of acceleration due to gravity is meter per second square. So overall unit for specific weight becomes kg per meter square second square. So dimension for specific weight is m into L to the power minus 2 into t to the power minus 2. So that is the dimension for specific weight. Next, dynamic viscosity mu. So unit of dynamic viscosity or coefficient of viscosity is Newton second per meter square. So Newton, you know how to replace, that is from Newton's second law of motion, F equal to ma. So alternative unit for Newton is kg into meter into second to the power minus 2. So into second divided by meter square, that gives unit for dynamic viscosity. Now unit of force is kg into meter per second square, that's what I told. So now unit of dynamic viscosity is kg into meter into second to the power minus 2 into second divided by meter square. So upon simplification we get unit of dynamic viscosity as kg per meter second. So dimension becomes replacing kg by capital letter M, meter by capital letter L, and second by capital letter T, and taking meter and second to numerator, it becomes kg into meter to the power minus 1 and second to the power minus 1. So dimension becomes M into L to the power minus 1, T to the power minus 1. So there is a dimension for dynamic viscosity. Next, pressure intensity P. Your unit is Newton per meter square. So there is a pressure that is given by force by area, normal force acting on a cross sectional area, or simply area. So Newton per meter square, unit of force is Newton, area it is meter square. So overall unit for pressure intensity becomes Newton per meter square. So dimension of force is M into L into T to the power minus 2. Therefore dimension of pressure intensity is M into L into T to the power minus 2 divided by L square, because unit of pressure is Newton per meter square. So dimension for pressure intensity is M into L to the power minus 1 into T to the power minus 2. Next, modulus of elasticity, that is represented by capital E, or bulk modulus represented by K, capital K. So unit of this bulk modulus or modulus of elasticity is same as that of pressure intensity, that is Newton per meter square. So dimension of force is M into L into T to the power minus 2. Therefore dimension of modulus of elasticity is, or bulk modulus is, M into L into T to the power minus 2 divided by L square, because unit is Newton per meter square. So overall dimension becomes M into L to the power minus 1 into T to the power minus 2. So that is the dimension for modulus of elasticity or bulk modulus. Next, surface tension sigma. First we have to know what is surface tension. Surface tension is the force acting per unit length. So unit becomes Newton per meter. So because force has a unit Newton, per length means length as unit meter. So Newton per meter is the unit for surface tension. So dimension of force, as we all know, M into L into T to the power minus 2. So therefore dimension of surface tension is M into L into T to the power minus 2 divided by L, because Newton per meter. So it becomes M into T to the power minus 2. Then shear stress tau. So unit is Newton per meter square, same as that of pressure intensity, or it is a like normal stress also same unit, Newton per meter square, force by area. So dimension of force is M into L into T to the power minus 2. Therefore dimension of shear stress is M into L into T to the power minus 2 divided by L square. So it becomes M into L to the power minus 1 T to the power minus 2. Work or energy, that is represented, work is represented by capital letter W and energy is represented by capital letter E. So unit of work is joule or Newton meter, because work is given by force into displacement. Unit of force is Newton and unit of displacement is meter. So Newton meter or joule. So dimension of force is M into L into T to the power minus 2. In order to get dimension for work or a unit for work, we can write like Newton meter. Dimension of force is M into L into T to the power minus 2. So unit of work, we are going to get it as Newton meter. So Newton meter, so dimension of work or energy is M into L into T to the power minus 2. In place of meter we have to replace by L. So M into L into T to the power minus 2 into L. So that is equal to ML square T to the power minus 2. There's a dimension for work or energy. Next, power. So power, as we all know, there's a rate of change of work. So that is represented by capital letter P, or work by time. So unit of work is watt, or unit of power is watt or joule per second or Newton meter per second, because work has unit Newton meter divided by second, that gives power, or joule per second, otherwise it is called as watt. So dimension of force is M into L into T to the power minus 2. Therefore dimension of power is ML T to the power minus 2 into L, because force into meter divided by time, that is a power. So M into L into T to the power minus 2 into L divided by T. So that is equal to ML square T to the power minus 3. Next, torque, that is represented by capital letter T. So it is given by force into distance or force into radius. So force as unit Newton, radius as unit or distance as unit meter. So unit is Newton meter. It is same as that of work or energy. So dimension of force that is for Newton is m into L into t to the power minus 2. Therefore dimension of torque is m into L into t to the power minus 2 into L. So that is equal to ml square t to the power minus 2. Next, momentum, or it is called as impulse. So that is represented by capital M. So that is given by mass into velocity. So unit of mass is kg, unit of velocity is meter per second. So your overall unit for momentum or impulse is kg meter per second. So dimension of momentum is m into L into t to the power minus 1, replacing kg by capital M, meter by L, and second to the power inverse by t to the power minus 1. Dimensional homogeneity. So what is dimensional homogeneity? So dimensionally homogeneous equation. So that means dimensional homogeneity means the dimensions of each terms in the equation on both sides should be equal. That means in order to have same dimension on both sides of the equation, unit on both sides should be equal. That is left hand side should be equal to right hand side unit, or left hand side dimension should be equal to right hand side dimension. The powers of fundamental dimensions, that is L, M and T, on both sides of the equation will be identical for dimensionally homogeneous equation. Such equations are independent of system of units. So that's what the powers of M, L and T, those are called as fundamental or primary quantities, should be equal on both sides of the equation. Then such equation is called as dimensionally homogeneous equation. So let us consider the equation for velocity as v equal to square root of 2gh, where unit of velocity is meter per second. So dimension of LHS. So what is the dimension of LHS? There's a velocity. For meter it is capital letter L, and second it is T, L by T. So L into T to the power minus 1, there's a dimension for LHS. Then unit of G on RHS is meter per second square, because it is acceleration due to gravity, and H, that is the height or head, that is measured in meter. So dimension is L. So dimension of RHS equal to square root of 2gh. Thus for 2gh we have to calculate square root of 2gh, we are supposed to calculate dimension. So that is equal to 2 is anyhow constant. Dimension of G is meter per second square is the unit. So L by T square into H, that is measured in meter. So dimension becomes L. So L by T square into L. So that is equal to square root of L square divided by T square. That is equal to L by T. Or that is equal to L into T to the power minus 1, taking T to the numerator. Then dimension of LHS is equal to dimension of RHS, that is equal to L into T to the power minus 1. So dimensions are equal and units are equal on both sides. So equation V equal to square root of 2gh is dimensionally homogeneous. So it can be used in any system of units. So it is dimensionally homogeneous equation, and it can be used any system of units like CJS or MKS unit. Check whether the following equations with their usual notations are dimensionally homogeneous or not. So let's check the dimensional homogeneity of following expressions. First one, HF equal to 4f LV square divided by 2GD and P equal to gamma QH. This was the question asked in June-July 2019. So solution. First let's consider first expression, HF equal to 4f LV square divided by 2GD. So 4 is a constant anyhow, so it has no unit, no dimension. F, it is a friction factor, so it has also no dimension, no unit. So L is the length in meter, V is the velocity in meter per second, G is acceleration due to gravity in meter per second square, D is the diameter in meter. So first let's consider unit of LHS. So this is the head, that is, or head height, it is measured in meter. So dimension is capital letter L. So unit of RHS, so that is for 4f LV square divided by 2GD, 4 by 2, that is anyhow constant, again into F, there is a friction factor, that is also constant. So unit for L, that is meter, and velocity, that is meter per second, so it is square actually in the problem, so meter per second whole square, divided by unit of G is meter per second square into unit of diameter is meter, so meter per second square into meter, so that is equal to meter cube per second square divided by meter square per second, so it becomes meter square per second square, that is equal to meter. So dimension of RHS is equal to L. As dimensions of LHS and RHS equal, the equation is dimensionally homogeneous. So equation as units of both the quantities, right, LHS and RHS quantities same, and so as units are same, dimensions also same. So that's the equation is called dimensionally homogeneous equation. So next expression for power, gamma into QH. So gamma, there is a specific weight or W, rho g, it is given by rho g. So rho g into QH. So let's first calculate the unit of power. Unit of power or unit of LHS equal to P, that is watt, or that is equal to joule per second or Newton meter per second. So Newton, unit of Newton, alternate unit is kg meter per second square from Newton's second law into meter divided by second. So overall unit for power becomes kg meter square per s cube. So dimension of LHS equal to ml square t to the power minus 3. Similarly, unit of RHS, that is for gamma into QH or rho g QH. So unit of rho is kg per meter cube, g is meter per second square, q is meter cube per second, and h is meter. So kg meter square per second cube upon simplification. So dimension of RHS, replacing kg by capital letter M and meter square by L square and second cube by T cube. So dimension becomes M into L square T to the power minus 3. As dimensions of LHS and RHS is equal, the equation is dimensionally homogeneous. So dimension is equal on both sides. So it is that equation is dimensionally homogeneous. Next, let us consider one more example for expression for capillary rise. So H equal to 4 sigma cos theta divided by gamma d. So sigma is surface tension, cos theta, that is the theta is the angle between a glass tube and water level, and then gamma is specific weight, d is the diameter. So and h is the head or height rise or capillary rise. It is related to capillary rise, so it is height rise. So h equal to 4 sigma cos theta divided by rho g d. Unit of h, that is measured in meter, so it is meter only. Then dimension of LHS becomes capital letter L because unit of h is meter, so dimension is for meter it is L. So unit of sigma, that is Newton per meter, so it is a force acting per unit length. So unit of density is kg per meter cube, and unit of g is acceleration due to gravity is meter per second square, and d is meter. So unit of force is kg per meter seconds to the power minus 2 because F equal to me. Therefore unit of RHS equal to kg meter into s to the power minus 2 into meter to the power minus 1 divided by kg into meter to the power minus 3 into meter into s to the power minus 2 into meter. So upon cancelling similar terms or common terms, we get value of RHS equal to m. There's a meter. So dimension of meter is capital letter L. So as we can see, LHS equal to RHS dimension. So equation H equal to 4 sigma cos theta gamma d is dimensionally homogeneous. Don't forget here 4 is a constant, as well as cos theta also constant value. So there is no dimension for 4 and cos theta. So there's a important step or important thing in this formula. Next, advantages of dimensional dimensional analysis. So some complex problems from fluid mechanics are simplified using dimensional analysis method. So we can solve some complex problem that may be related to flow or that may be related to heat transfer. Anyhow, we are not going to consider heat transfer here. So problems related to fluid flow can be solved using dimensional analysis. Then it gives functional relationship between variables in dimensionless terms. So functional relationship between variable means independent and dependent variable in terms of dimensionless terms, that is pi terms. About pi term we are going to discuss. I am going to discuss about pi term in Buckingham's pi theorem. So it reduces number of variables involved in physical phenomenon. So we can greatly reduce number of variable by replacing ratio of variables by some dimensionless parameter, that is phi. Then the dimensionless parameters are used to make certain logical deductions about the problem. So we can arrive at some expression or some logical relationship using dimensional analysis. For example, Reynolds number expression, that is given by product of Rundle number and Nusselt number, that is from dimensional analysis only. So those are the advantages. Then applications of dimensional analysis. It is used to check dimensional homogeneity of the equation. We already used this application part. So in order to check whether given equation is dimensionally homogeneous or not, we can go for dimensional analysis. Next, it is used to derive equations for phenomenon in terms of non-dimensional parameters like Reynolds number, Mach number, etc. So we can derive expressions for dimensionless terms like Reynolds number, Froude number, Weber number, Mach number and all using dimensional analysis. Then it reduces the number of variables in a problem by grouping them in less number of dimensionless groups, which reduces the number of tests in model analysis. So it is going to reduce number of step or number of it reduces number of tests or number of steps in model analysis, that is related to performance test of model with respect to an prototype. So we can greatly reduce the time in testing of the models. So it is used to arrange the test in a model analysis in a systematic manner. This makes the test more economical and less time consuming. By using this dimensional analysis, we can make the test in a systematic manner, and it results in some less time parameter, and it is a more economical when compared to other tests. So these are the applications of dimensional analysis. So today we discussed about introduction, then primary quantities, then secondary quantities, then dimensionally homogeneous equation, application, and uses of dimensional analysis, or applications or uses of dimensional analysis, and advantages. So advantages of dimensional analysis is very important. So next video I am going to explain about solving of problem using Rayleigh method. Okay, thank you.